Nice to meet you. I'm Paulo Brás. I am a researcher for the LZ experiment mainly. I've been working in different projects, but really my main focus is with this LZ experiment. And I will be talking about essentially the endeavors of the LZ experiment on the search for dark matter. But as Andre pointed out, my expertise and really most of my focus in LZ was up until very recently in nuclear physics and neutrino physics with the neutrino stellar decay searches. But ever since I deviated from my course and I delved into the dark matter side, and that eventually led me to the position that I'm in right now. So let me give a quick presentation of the LZ collaboration. So this is a collaboration of 38 institutions, around 300 people, scientists, engineers, technical staff, and lots of students. We are essentially spread out across multiple continents, and we very often join together to collaboration meetings and stuff like that. This was not the last one. Unfortunately, the last one I don't have pretty pictures of. But yeah, so this is a very big, healthy collaboration. Many people with lots of expertise, and as I will show in a couple slides, this is because there's a lot of physics that you can do with these type of detectors, and there's a lot of physics to explore in this experimental endeavor. All right, so just to give a quick context on like the history of dark matter and why this is so important. So starting in 1933, Fritz Zwicky, which kind of coined the term dark matter, noticed there was a large discrepancy in mass when trying to calculate the mass of the coma cluster. It was trying to use different methods, so looking at the luminous contents of the stars and the galaxies, and the kinematics, the movement of the constituents of the cluster, and the numbers that he was getting were very very different in some orders of magnitude actually, and that kind of sparked like a doubt. So maybe the luminous matter, which wouldn't account for all of the mass that was assumed from the kinematics, maybe there was a component that was non-luminous, which he called dark matter. This was also further noticed in different other clusters, in particular very noticeably in the Virgo cluster by Sinclair Smith, which was a colleague of Zwicky. And essentially, this was an oddity at the time. This was very early in this type of beyond the Milky Way nebula astronomy, and so this was not like picking much attention of the scientific community. But then in the late 50s, because of Victor Ambartsumian, we had like a revival of this issue, and it was really trying to fuel the debate with this type of issue with this dynamical anomaly in the cluster mass determination, and this led to two very important conferences that were like sparking this issue, and then almost at the same time, a very important, tremendously important contribution from Vera Rubin. In particular, of the many works that she did, a very important one was like the measurement of several galaxy rotation curves. So the velocity of the stars in the galaxy as a function of the radial distance, and almost always you would see or something that it was not really what you would expect from Newtonian dynamics and from the inferred visible matter in the galaxy, kind of hinting at a dark matter halo that envelops the galaxy and kind of dominates the mass of the galaxy beyond the galactic disk. So yeah, this pretty much cemented that something was off. There were other contributions, but these were like definitely the main ones. Briefly, I've kind of explained like this galaxy rotation curve. So around 1980s, we had innumerable measurements of these types of galaxy rotation curves, and all of them systematically show this. And this kind of only really was explained by two phenomena. Either the Newtonian dynamics was insufficient, which we definitely still credit. It might be the case that Newtonian dynamics at these scales is not particularly good at understanding how the kinematics works, or there was some missing mass in the system. So this is the premise that I'm going to push in this presentation, obviously, because this is what dark matter is supposed to be there doing. There are other very important observations involving other gravitational effects from dark matter, obviously, that kind of picked up this very important debate between either modifying Newtonian dynamics or missing matter, and this is gravitational lensing and also the cluster collision observations. So we have a lot of different cluster collision observations, for example, famously the bullet cluster, where you do see that, for example, when two clusters pass through each other, you kind of have a detachment between where the majority of the mass is and where the majority of the intergalactic dust is. So essentially, this means that it's not the non-luminous regular matter that seems to be contributing to the majority of the mass of a system. It's something else. And that something else is still not compatible with the luminous matter that goes through, and it seems to be something that is not significantly interacting either with regular matter or with itself, which again is a very, very important point. So I won't go through all of these observations because I really want to just give an overview of this dark matter paradigm, but I will mention very importantly that there is a strong consensus in favor of dark matter across many different observations at many different scales of the universe. So I did mention this first too, but beyond the galaxy and the cluster of galaxy scale, you have large-scale structure formation based on our understanding of how the universe evolved and how the large-scale structures of the universe would form. Really depends on the existence of a large quantity of a specific set of a matter with a specific set of properties, mainly that is cold, and I'll get to that in a second. There's also the cosmic microwave background, obviously, because it kind of reveals what was the universe's content by species at the beginning of the universe, and how that would then result at the time of last scattering of the formation of these anisotropies in the early universe, and Big Bang nucleosynthesis, which is also an avenue to the ratio between radiation and matter in the early universe. So all of these observations are really pointing to a very specific set of parameters, and those parameters are consistent with a very large matter content, but not a very large baryonic matter content. I put here a plot from Planck 2018, just showing that the very strong constraint of a lot of different observations that I mentioned above, and really pointing to a very specific value of the matter density. I also made the point to show this because there is kind of a tension between what the early universe says the Hubble parameter is and what we currently see. So maybe another crisis in cosmology in tandem with the dark matter hypothesis. Well, yeah, I'm not going to comment too much on that. I just wanted to mention this because like a month ago, there was this very interesting observation for the baryonic acoustic oscillations from Decay, which kind of hints that maybe there is some time evolving dark energy component to the universe. So the universe is a bit more dynamic than what we think. And maybe that will wash off this distinction between measuring the Hubble parameter early in the universe and now. Not going to go too much into detail, but I find this really, really interesting. So this is still an ongoing effort to try and understand how the universe works. But currently, really the best model that we have for cosmology is this lambda CDM model. Lambda standing for dark energy, which is another issue in itself, but CDM is for cold dark matter. And really this is kind of the ingredient that matters here for our purposes, because really this means that the universe is really dominated by dark matter and dark energy. So regular matter really doesn't contribute much. In more importantly, it seems all of these evidences seem to indicate that dark matter represents around 84% all of the matter in the universe. So like distilling this into a bit more simplified way. So of all of the content of the universe, really we are only 5% that we really know. And I find that really interesting and really scary, but that's really the kind of the motivation of what we want to why we want to study this. So what could dark matter be? So we have this kind of observables that we anchor our hypothesis for dark matter. So it does not interact with light. It's implied only by gravitational effects, is nearly collisionless. It must be stable in the timescale of the universe because it contributes to the universe's dynamics and large structure formation. So it needs to be around for a long time, or dynamically produced, but that's a whole different issue. It's non-relativistic, again, cold because we need large structure formation to be the way that we observe. It needs to be abundant because we measure it to be abundant, and the local density should be relatively large. So of all of these things, I think we can all agree that most of the standard model particles are kind of excluded from being dark matter. There is this tiny exception that neutrinos do fit a couple of these parameters, except this fifth one. So they do contribute as hot dark matter, but they cannot explain the full dark matter content. And just to make that point a bit more clear, which is something that is often omitted, and as Dennis here puts it, lots of things are invisible, but we don't know how many because we can't see them. And as we can't see dark matter, it doesn't mean that it's just one thing. It could be a lot of things. It could be an entire different dark sector that we just are not able to get a tunnel to our standard model sector. And definitely dark matter is a mixture of many things, and we definitely know that neutrinos are one of those things. So the best formal definition that we can have right now is a hypothetical substance that is massive, stable, or long-lived, chargeless, and weakly interacting. So there are a couple of candidates that fit this criteria from different beyond the standard model hypotheses. They're kind of all over the place. Really, we have no sense of this. The mass scales are all over the place, and it can go from things that are very, very light to very, very heavy. But mainly, like the main candidates for dark matter can really be summarized as axions, which is a very, very strong candidate because it essentially stems from QCD and a very interesting observation of the lack of symmetry breaking in quantum chromodynamics, which kind of leads to this axion as being a very favored dark matter candidate. Axion-like particles is similar, but just a more generic class of particles to the same sense. So these are very light candidates. We also have dark photons. You have obviously neutrinos, which we know that contribute. We have the sterile neutrino. If it exists, is a mess because we definitely can observe it without with the regular channels that we use to observe these types of things. We have the weakly interacting massive particle, which really is a generic class of particles, and I will focus a bit more on this because this is the goal of LZ and most of the experiments of direct detection in tandem with axions, for example. You also have ultra-heavy dark matter, so a lot of different models can give things that are really beyond the scale of the WIMP. And you also have this type of class, massive compact halo objects. So these are not really exotic matter. This is regular matter. These are just objects that don't emit light. For example, primordial black holes or black hole remnants or brown dwarf stars, stuff like that. They do contribute. They are very tightly constrained in the contribution, and they can definitely not explain most of the observations for a non-baryonic component of dark matter, but still, it's a contribution. So in the case of the weakly interactive massive particles, I will make the argument here that this is probably still one of the best motivated dark matter candidates. Its potential origin could be as a thermal relic from the Big Bang, which if we go through the electroweak scale, it really gives you a very specific set of mass ranges between MeV to TeV scale. And a cross section that is really within grasp of what we could potentially aim to detect at the moment. So this is also one of the reasons why it's very interesting to look for this particular candidate, because it's really in our grasp with the current technology that we have. There are several standard model extensions that really naturally produce WIMP candidates or light stable particles that can be WIMP-like and that would fit this role very well. A couple of supersymmetry models were initially very motivating for this type of thing. Unfortunately, supersymmetry kind of fall a bit of grace with time, but still we have a lot of different models that we can potential probe. And really, I would argue that with the current technology that we have, and as well I will explain, LZ will fit into that category, we are really probing the most interesting phase space that we can at the moment. Right, so how can we aim at detect dark matter? So if it's something that is weakly interacting, if it's something that is very complicated to even assess its existence, really, how can we aim at detect such a thing? So really, we have three channels that we can explore. So we have particle colliders. We can see if we could produce it. If there is a tunnel between this dark matter sector and the standard model sector, it might just be that we could produce dark matter in these very high energetic collisions that we can get in our particle colliders. And really, LHC is already covering the most interesting mass range, for example, for the WIMP. So looking for dark matter in these detectors will essentially amount to looking for missing momentum, because once the particles are produced, they wouldn't be detected. But the signature of them being created would be on our reach. There's also the prospect for indirect detection. So essentially, we even if the dark matter particles, if it is a particle, it's stable, it could self-annihilate or could have like some sort of annihilation channel. And if it's not stable, if it's just stable on the timescale of the universe, it could decay. So it could produce secondary particles. Some of those particles could even be standard model particles. So we could look for dark matter by looking at regions where we know that dark matter density is very, very high. And we could try and see if we can detect an excess that is consistent with what would be an annihilation or decay product of a dark matter particle, which would be as a very specific signature for most of the models. There's also, in the case of the axion, we could have because of the nature of the axion, there could be like an axion wind or an axion flux coming from the sun, for example, which is something that a lot of interesting axion experiments are searching with these types of helioscopes that try to look at the sun and see a flux of axions where essentially no photons could reach the detector, but axions could, because they are weakly interacting. And obviously there's the direct detection mode, and I will focus on this because this is really what LZ strives for. And this is essentially just putting a detector on the Earth, and the Earth is going through the galactic dark matter halo, if it exists. So there's a possibility of a dark matter particle interacting with a baryonic particle or regular nuclei and producing a signal. This could also be the same for axions. For example, the axions coming from the sun, they could be detected by axion conversion in resonance cavities. and stuff like that. So really, direct detection is you build a detector, you put it here, you make sure that you shield it from everything else that could produce a signal similar to what dark matter would produce, and you just wait and see if you can find something. So on the case of WIMPs and really direct detection of WIMP dark matter, in any sense, really stems from this particular fact that the Earth and the Sun are moving around the Milky Way and around this dark matter halo that we expect to be present in our galaxy and can really enveloping all the galaxy. And as we travel along, really we would expect to feel some sort of WIMP wind because of this motion, right? So essentially, this produces a flux of this WIMP particles in the Earth and at a detector. And even though this is a very rare process with a very, very small cross-section constraint, because really we don't observe dark matter interactions that often, we still can aim to try and detect something. So there's a couple of things that we need to be painfully aware of. So the cross sections are abysmally small. This is non-relativistic dark matter, so really the scattering will be producing a very small energy deposition in the detector. So low thresholds in the detectors are essential. And really, the kinematics, given the mass range that we expect from WIMPs, really favors the interactions with the atomic nuclei and not the electrons. So which is another hindrance. So let's put this in some perspective, some numbers. Given the current best limits, which is the result that I will, spoiler alert, I'm going to talk here about LZ. For a xenon target, which is what LZ uses, for WIMP mass of around 36 GeV, so a middle of the road kind of WIMP mass, and for the local density that we kind of together decided that is the value that makes most sense from observations, and given the Earth's velocity in the halo, we get a rate of around 1 event per ton of xenon per year. So a 10-scale xenon detector waiting for a year would not expect to see much more than 1 event, of the order of 1 event. So really, really rare. And that energy deposition on average would be of 6 keV, which is again very, very small energy deposition. So it's imperative that we have a detector that's good enough to kind of see these. There are other requirements that are really, really important for this type of search. Obviously, stemming from the fact that this is a rare event and from the fact that this is a very low energy interaction that we would expect from the signature of dark matter, we really cannot afford to have a detector that is constantly bombarded by background radiation, because background radiation is everywhere. So we really need to ensure that we know and understand how to mitigate essentially our backgrounds. So the experiment needs to be ultra low background in order to be able to have a chance to see these types of things. So if if a dark matter interaction is a needle in a haystack, we really, really should try to remove as much hay as possible. So a couple of things that we definitely have to do. So we have to move underground because we need to shield from cosmic rays. So the Earth is constantly bombarded by cosmic rays. Cosmic ray muons have a high penetrative power, so we definitely need to make sure that we are far away from the surface as possible. We need to build the detectors with very high radio purity materials, because otherwise you would be contaminating the very core of the experiment, and that will definitely hinder any potential observation. You would have to deploy passive and active shielding. Obviously, this is kind of the example that I show here for passive shielding of the xenon itself. Fortunately, xenon is an excellent target because it's very dense, so it produces like a self-shielding, meaning that the center of the detector is really much quieter than the extremities because of the radiation attenuation. And then as an example for LZ, you kind of get like around 4 orders of magnitude on a couple on like half a meter of a detector extent. So really good passive shielding, and not just from the xenon itself, obviously from materials surrounding the detector. Active shielding, for example, vetoes. Deploying vetoes is definitely something that is encouraged for these type of searches. Other things that are very important: position resolution and fiducialization, again, to be able to work out the position in order to make sense of that self-shielding, and obviously to reconstruct your background position distributions and stuff like that. It's very important. And energy resolution and threshold, as I mentioned, we are really looking at very small energy deposition, so this is essential as well. So more on xenon, why is it so interesting? So most of the things that are really interesting about xenon is it has a high ionization and scintillation yields. So this is very good because this means that you can have lower thresholds. So at a given energy deposition, you're more prone to see more quanta produced that will effectively mean that you can see smaller energy depositions. Importantly, it's transparent to its own scintillation light. This is obviously very important because if you are looking at scintillation from an interaction, we have to have a chance of actually seeing it. Very easy to purify, very high atomic mass, which is very good because the cross section of the coherent WIMP nucleus interaction is proportional to the square of the atomic mass. It's very easily scalable. These are liquid noble gas detectors, so it's very easy to scale a type of detector like that. And it also has the bonus of doing some other physics, and I put this here because this is really my bread and butter and really one of the things that I did most extensively in LZ, looking for these neutrinos and two neutrino double bed decays from some xenon isotopes. All right, so now going into the LZ detector, the LZ experiment. So this is really not just a dark matter detector, even though that's what we call it. This is a rare event observatory, so we can do lots of things. You can do dark matter, you can do rare xenon decays, as I mentioned. You can also do neutrino physics, and obviously searching for axions as well. So the core of the LZ experiment is a 7-ton dual phase liquid xenon time projection chamber, and this is something that I will briefly mention how the construction works and how the detector works, but essentially it's just a large bucket of xenon that is observed by arrays of photomultiplier tubes or light sensors on the top and on the bottom that really try to capture as much light from an interaction in the xenon as possible. There are two additional detectors that are very important, which we usually call them veto, but they are detector on their own. It's this 2-ton liquid xenon skin that surrounds the TPC, which you can't really see here, and a 17-ton gadolinium-loaded liquid scintillator outer detector, which is in green in this diagram, which is very useful for neutron veto, because neutrons will produce an indistinguishable signal from a WIMP interaction with the nucleus, because neutrons will essentially scatter with nuclei mainly, so they will produce an event signature that really closely resembles dark matter. So we really need to make sure that we understand our neutron background and we can thoroughly mitigate it. So this auto detector is mainly for that. And all of this instrumentation is submerged into a 200-ton water tank, very high purity water, that also works as a muon veto. So it has the same readout as the outer detector, but if a muon eventually crosses the detector, we have the ability to look for the Charriot Cobb light that is produced. So it's again a very important thing to be vetoing these muons. So the LZ experiment is installed at the Sanford Underground Research Facility in South Dakota in the beautiful, beautiful Black Hills. So this was the Homestake gold mine, a former gold mine, where the Homestake experiment that gave us the solar neutrino flux was installed. This is a 1.5 kilometer underground laboratory. So this essentially means that we can have a 10 to the 6 muon attenuation, which is really, really welcome. Essentially, the construction of the TPC of LZ it has several different components. I'm kind of gonna go from the bottom up. So the whole thing, because we are dealing with liquid noble gases, is kind of encapsulated in a cryostat vessel to allow us to get to essentially 170 Kelvin, which is really the type of temperatures that we need to have at 1.8 bar for getting like the stable liquid xenon phase that we need. I did mention that this is a double phase TPC. It means that we have both liquid and gas in the detector. So we have a liquid phase in this main target region where an electric field is maintained by a couple of grids. But we also have a gas phase at the top with a couple more grids and a very strong extraction field region, which essentially encapsulates the liquid surface, so the liquid-gas interface. And this is going to be apparent in a second, but this is for us to produce an electroluminescence signal in tandem with a scintillation signal from the primary scintillation of an interaction with the liquid. So the whole thing is essentially covered with this PTFE light reflector. This is to ensure that any light that is produced in the liquid xenon is captured and has a chance to be observed. And you can kind of see here like the PTFE tiles that are surrounding the TPC. These are the PMTs. This is the top PMT array. The bottom PMT array you can see, well, you can see in here. So the whole thing is observed by essentially two sets, top and bottom, of 494 total PMTs. And as you can see, even in the places in between the PMTs, you have this reflector because it's really important. So all of these materials are high purity, and as you understand, this is very important. As you can see, you have a lot of different pictures of like everything is covered in white, everything is covered with this PTFE reflector. In this case, this is the skin, the skin space. So this is in between the light reflector cage that I've shown here before and the inside of this cryostat vessel. So there's a lot of displaced xenon there. So we kind of use that as a veto because that xenon will also see light when an interaction happens there. And it's an actually very good anti-coincidence for gamma rays. It is instrumented with 131 PMTs, if I'm not mistaken, and it has a very decent threshold of 100 keV in most of the volume. So it's a really good gamma threshold, gamma veto. And we also have the outer detector, which you can kind of see in this image. This is the water space, and these are the acrylic vessels that contain the gadolinium-loaded liquid scintillator. And essentially, this is an active veto for gamma rays and for neutrons. So gadolinium has a high neutron capture cross-section. So it produces a very clear signal. So we definitely see when a neutron is captured by the gadolinium. It can also basically be captured by hydrogen in the liquid scintillator, which will also produce a very characteristic signature. So given the high scintillation yield of this liquid scintillator and the light collection that we have, really we have a very high veto efficiency and more importantly, neutron veto efficiency and muon veto efficiency. All right, so now a bit on explaining how the actual working principle of the TPC is. So essentially, we are looking at two sets of signals from the scintillation and from ionization. This is just a very useful schematic. So when a particle interacts in the liquid xenon bulk, it will produce both scintillation and ionization. We do detect the scintillation immediately as this S1 signal, which is a very small signal. But then because we have an electric field, those ionization electrons will be pushed to the top of the detector, where they will be extracted to the gas phase by a very strong extraction region field. And they will produce in the gas a very strong electroluminescence signal that is then captured mostly in the top array. And this is the S2 signal that we call here, which is much larger than the S1 signal. The important thing here is, see if I can go back a bit forward. The important thing here is that with these two signals, we essentially can reconstruct the full event. So the deposited energy is given by essentially the gains from these S1 and S2 signals. The position, the depth of the interaction is given by the time difference between the S1 and the S2, because essentially that gives you the time that it took the electrons from reaching the liquid surface of the TPC relative to the timing of the S1, which is really the timing of the interaction. And the XY position is reconstructed by the S2 signal and the pattern that it produces on the top array. You have an example here of an interaction that was around this position in the detector. So really, you can have a full 3D reconstruction, and you can have, because of a very good light yield, scintillation light yield from liquid xenon, you could have a very good threshold. So the way that we monitor and calibrate the detector is essentially by deploying different sources, and most importantly, because electron recoils and nuclear recoils produce different signatures, we do definitely need to calibrate both. So electron recoils, or a recoil that happens with the electron of a xenon atom, often produces more ionization compared to the same level of scintillation. So in this type of very handy plot that will be used extensively from here on out, in the x-axis you have the strength of the scintillation signal, and on the y-axis you have the logarithm of the strength of the ionization channel, essentially. And as you can see, the electron recoil band in blue has, for the same amount of scintillation, much more ionization than the nuclear recoil band in orange. And this is something that we explore as a discrimination, because if most of our background will produce electron recoils, namely from betas and from gamma rays, from decays within the detector and from external sources, but our signal will mostly produce nuclear recoils, then really we have a very good signal to background discrimination by having this ER leakage rejection, which is very, very high, because these are really, really well separated. And the separation depends on the field strength and other parameters of the detector. But really, LZ and similar experiments can really get a very, very high rejection of electron recoils from this technique. So really, this is the space that we use for our inference, for our analysis for the WIMP search, at least. Is this S1 and S1 versus S2 space. And for example, for calibrating it, to ensuring that our detector really has a very well calibrated response in this space, we deploy several sources. Two that are presented here are a tritium source, which really maps very well this low energy, a couple of keV region of this S1, S2 space. And we have this DD, deuterium neutron generator, that also really covers very well this energy range. We also deploy several other sources, but these are kind of the main ones that we use to produce this kind of signature and calibration. We also use the background signal that we get from background radiation to calibrate the detector, and mainly to understand our G1 and G2 gains. So these are the scintillation and ionization gains. And these are really very well constrained, and essentially this allows us to have a very good energy resolution, and in particular at the high energies. So in the energy range that really interests me on the neutrino stable decay side, really the energy resolution can be as low as 0.64%. And I remind you, this is a very large detector, and this is unprecedented energy resolution for this type of detector and for this range. This is really, really good to always present on behalf of LZ, because this is really something that is very close to the maximum resolution that we can get with this type of detector. Obviously, in order to understand how our detector works, and most importantly to model our backgrounds, we definitely need to have very strong simulations. So for example, for the WIMP searches, there are really a variety of very important backgrounds that are relevant for these searches, mainly the lead-214 beta decay. This is coming from the radon. So radon is something that is in all materials, and it kind of emanates to the detector. It mixes well with xenon. You cannot remove it because it's not electronegative, so there's no sense of removing it. So this is a constant background that we have, which really, the only way that you can really do this radon mitigation is to try to have chromatography purification on the spot, which is something that we actually do, to try and separate the radon from the xenon and also the krypton. But you definitely need to make sure that your detector is clean. But this is something that is unavoidable to some extent. You have also a couple of dissolved electron capture decays. These are very special because given the nature of this electron capture, really the response on the detector is really not close to an electron recoil response. It's more close to a mix between electron recoil and nuclear recoil. I will talk about that later a bit. So this is a very tricky background to check, and really we are only now able to even detect these types of decays in these types of experiments. So it's really exciting. Then you obviously have like long-lived gamma emitters, mainly from the uranium and thorium chains, potassium and cobalt. These are in all of the materials that you can think of. Then you have your neutrons from spontaneous fission, mostly from radioactive contaminants on the materials as well. And you then have your cosmological sources like solar neutrinos and atmospheric neutrinos and stuff like that. And you have these accidental coincidences. I won't go into much detail on this because these are just detected effects, really. A pair of S1 and S2 signals that are uncorrelated. Essentially, they are not from a real interaction. They are just spontaneous signals in the detector that are paired up in a way that look like signal. Fortunately, we can mitigate or describe this very well because some of these will be happening in an unphysical drift time, meaning that they will definitely not be physical in a sense that they are reconstructed outside of the maximum range of the detector position that we should be able to see. So this is a kind of a sideband that is very useful to try and understand how these accidentals form and what their shape should be. So these are very, very tightly constrained for our WIMP search analysis. So eventually we pair this background modeling and simulations to get this very detailed background model across many different energy ranges. And then we use this to constrain our backgrounds in our WIMP search region. So these are very well, very strongly constrained. And I have here like a separation between radon tagged and radon untagged. This is something I will talk in the next slide, which is also very exciting. And essentially this whole thing is because of the nature of this detector. This is a liquid detector, and because xenon is so dense, and because you have a very good control of the temperature of the detector, you can essentially make different mixing states of the detector. And I won't go into much detail, but essentially by changing thermodynamical properties, you can induce like a very chaotic, turbulent flow and mixture of the liquid xenon, or you can do like produce this very laminar, very convective cell-like flow in the detector. And what this state allows us is to follow consecutive decays. So one of the things that we use this for is to tag the radon daughter decays and essentially tag charged and neutral polonium beta decays in the detector. So this allows us for a significant reduction of the polonium background, but it also allows us to do these tagged and untagged samples that are then used for inference, because the tagged sample is a sideband to the inference to do the final analysis. And I will leave this on hold because this is a very interesting result that I will mention. And I will go through the other thing that I also mentioned, which is these electron capture backgrounds that are a mess. And essentially what this means is, because they are not really electron recoil-like or nuclear recoil-like, we have like a very specific response for these types of decays that is essentially between what would be the ER band in gray and the NR band, which is represented here by what a WIMP signal would look like. So they kind of transition between the two, and this is something that we need to measure. And we kind of measured it in this analysis that we did in this past 2 years, to be very tightly constrained to essentially a suppression factor of 0.70 for the 124 xenon decay, double electron capture decay LL shell. And this is important because, as I will mention next, this will seep into the WIMP region, and it's something that we need to take into account, mostly with this radon tagging. So very, very quickly, the next couple of minutes, I want to leave room for questions. I'll just mention this bias mitigation strategy that we do, which is something that is very different from what's usually done in this type of experiments. So usually, to make sure that you don't bias your results, what these experiments do, they essentially blind the signal region. And essentially that means that along the analysis path that you choose, all of the choices that you do are not informed by what you expect your signal to be, because that would be a very big bias, right? So you are always trying to make sure that you are not biasing the choices that you make in the analysis. And by that, some people decide to blind the signal region. So another strategy, instead of blinding the signal region, you could inject false signal that is really indistinguishable from real signal, as you would expect it to be. And essentially that will put you always like a step back in trying to understand if there is real signal or not, and really ensures that you are paying attention to everything and not just what you expect. The way that we do that is essentially we hijack a couple of events that are really not available to the analysis, and we use them to get an S2 signal from one event and pair it with an S1 signal from a different event in such a way that in this S1, S2 space, they will mimic what we expect from a WIMP signal. And we really make sure that we constrain the rate and energy profile of these based on the current best limits. And we also have like this flat step that we also consider. This is just for EFT analysis and stuff like that. But essentially, we used our previous limit, which was the best limit at the time, in the WIMP Search 2022 result from LZ, to constrain this rate. And we are now injecting these salt events randomly, given a specific rate and a specific energy. And this kind of puts us like on the fence to do our analysis, because the signal region is being permeated. Eventually, at the end of the analysis, when we are confident that we did a good job, we stop analysis development and we do the unsalting, which would be the same as unblinding, and we reveal what was salting or not, and then we can place our constraints on the results. All right, so now I'm just going to briefly mention the latest results from LZ, because these are really the world-leading results for WIMP search direct detection. So this is, I'm not going into the details. So this is our WIMP search region of interest. So this is where we expect most of our signals from a variety of WIMP masses to appear in S1 space and S2 space. We do some time exclusions because we need to remove periods where the detector is not stable, where we have some large S2s that produce a lot of light in the detector and produce all sorts of very complicated behaviors that we cannot reconstruct. This leaves us a very high percentage of lifetime. Over this, then we apply some S1 and S2 quality cuts, and this is basically to remove some pathologies that we, from calibrations, know that are not signal-like. And this is mostly related to accidental events. We obviously do a fiducial volume cut. As I mentioned before, really, we want to be looking only at the center of the detector where most of the external backgrounds don't reach. And we also have the skin and EOD vetoing most of the events at the periphery, and some that go a bit to the inside, again, to exclude some background further. And with that, this is the kind of the result that we had at the end of this WIMP Search 2024 campaign that we did. So we expected 207 ER counts, and we expected less than one NR count. This is constrained from coherent neutrino scattering from boronate neutrinos. And in our final exposure, we had 3.3 10 years of exposure. on these 220 live days that we had, we saw 1,227 events, so really, really close to what we expect. Then we did the unsalting, and we identified which events were salt, which were artificially injected. And once we removed them, we had these 1,220 events remaining, and we did the statistical analysis on this data set to infer if we did see something that could be WIMPs. So this is one of the things that I wanted to mention. So this is the radon-tagged and radon-untagged background. So essentially, this plot just shows polonium-214 decays, essentially. And this one shows a mixture of polonium-214 and other decays. And really, the most important thing here is this contour of essentially the xenon-124 mixed charge yield, charge suppressed decay that I mentioned before, that is really permeating the NR band at these higher energies. It is really not present here. So we tightly constrain this background, even though it's on top of the band that we expect the signal to be in. We really, really tightly constrained it because of this technique. So this is why the radon tagging is very useful. So at the end, we compare the background model that we had with our data, and the background only model really fits the data very well. So the best fit to the data is 0 WIMPs at all tested masses. So we definitely don't see nothing that is compatible with a WIMP signal. This is kind of the rundown of our background, measured background in this exposure. And with this, we can set an upper limit to the WIMP nucleon cross-section, spin-independent cross-section as a function of WIMP mass. And really, the upper limit is because we have some downward fluctuations, is power constrained at the -1 sigma sensitivity band, but it's given here in black, and really is a tighter constraint in all WIMP masses for the WIMP Search 2024 only. If we can combine all of the data that we have for LZ at the moment, so 2024 and 2022 campaigns, we have an even stricter constraint that is with a world-leading result at all masses. And we also have some spin-dependent WIMP nucleon cross-sections, which are also world-leading into some mass ranges. But really, this is kind of the final result from this campaign. So yeah, I'm not going to go through these conclusions. I'll leave room for some questions. Hopefully, I convince you that LZ is world leading in WIMP search, in a direct search of WIMPs and dark matter, and that we had some very exciting physics even in this WIMP search analysis. Mostly this first observation of charge suppressed xenon-124 double electron capture, which is really exciting. And we also had this amazing radon tagging capability and our unprecedented energy resolution, which really is something to be very happy about. After 5 years of data acquisitions, we get a very healthy detector that is really striving towards getting 1,000 live days in the next couple of years and doing a multitude of different physics. So yeah, thank you so much for listening. And